Okay, so what we're going to move on to in this lecture is further study of what I introduced at the end of the last lecture, this notion of what we call a critical point of a function. And critical points are important in this field called optimization. So optimization methods is an important area of computer science and one which you'll meet in modules in year 3. The particular topic I'm going to concentrate on is something called the second derivative test. So, critical points. What do I mean precisely by the critical point of a function? If you recall, in the introductory problem that we studied, which involved finding the maximum height that was reached by some object, and in that problem we knew that the height after a particular distance was given by some function. And we argued when we were looking at that problem that this maximum height, this was reached when the gradient of the line touching the point at the maximum height, when that gradient was 0. In other words, from what we saw when we introduced the notion of first derivative, that's the point at which the value of the first derivative of our function is equal to 0. So in general, a point, the input x, the value of the function at x, at which the derivative of that function, the first derivative of that function, takes a value 0, that is what we call a critical point of the function f. And analyzing critical points, this is an important mechanism in what I've referred to as optimization problems. So, here are some examples. A critical point can be a minimum value, as in this case here. It can be a maximum value, as in this function. A function may even have a mixture of minimum and maximum points. So here we have a local maximum value, and here we have 2 minimum values. So this function has 3 critical points. We can even have cases where we can't even classify what exactly critical points are. Okay, so if I look at those examples in a little bit more detail, what we see from them is that a function could have a single minimum critical point, could have a single maximum critical point. It could have a mixture of these, a mixture of local minima or local maxima. And finally, it is the case that our function could have no critical points at all. In other words, no value for the first derivative of that function under which the first derivative becomes 0. So really what we're going to be concentrating on, what we're interested in, is how do we distinguish these? How do we tell this case from this case from these cases? Well, the last case, that is actually quite straightforward in some ways. We can identify functions that fall into this category because those are just the functions which, when we form the first derivative of that function and we look for input values under which the first derivative becomes 0, then we can't find any. In other words, the identity, the first derivative of the function on an input value equals 0, that is no solutions. So that's the class of functions we find in this case here. For those in the third class, the mixture of minimum and maximum values, well, in order for a function to have both a minimum and a maximum, this identity must have at least two solutions. Okay? So two of those cases we can deal with. The other cases, the ones that are really of interest, we want to distinguish critical points that define minimum values from critical points that define maximum values. So how do we do that? How do we tell if a critical point, remember that is a value under which the first derivative of the function becomes 0, how do we tell if that's a local minimum or a local maximum point? In other words, the smallest or the largest value attained by that function in a particular range. Well, the main tool that we use is something that's called the second derivative test. So I'm going to describe how that operates. Right, so our starting point, we have a function. And if its first derivative exists, if it's well defined, well, the first derivative is also a function. And so in principle, we can think of taking the first derivative of the first derivative. In principle, there exists some object, which I'll use this notation to describe, and this object, just as we went from here to here, this object is also a function. So we can take its first derivative and continue taking the first derivative of that. So in principle, the process of taking the derivative of a function, the process of differentiating a function, isn't just a one-off operation. For many functions, we can differentiate the outcome infinitely often. So just as we had this dash style notation for first derivative, for second derivatives, as they are called, we use 2 dashes, third 3, fourth 4 dashes. That can get a little bit cumbersome, so another notation which is rather more common in this context is to use this form here. So if we have a fixed constant value k, we can describe the kth derivative of that function, not by simply writing f with a string of k dashes, but in this rather more convenient form here. So I mentioned this object called the second derivative test. What exactly is that? We start off, we have our function f. And the first thing we do is we construct its first derivative. We differentiate the function f. And then we find all of the cases, all of the input values under which the first derivative takes the value 0. The next thing, we form the second derivative of our original function. In other words, we form the first derivative of the first derivative of our function x. This is called the second derivative. So we can find out just by using exactly the same techniques that I described at the end of the last lecture. The next stage of the second derivative test, we take each of the values that we found here, each of the values we found in step 2, and we compute the value of the second derivative function on those inputs. And then, if that value is negative, it's something strictly less than 0, then that tells us that the corresponding critical point is a local maximum. If that value is positive, if it's strictly greater than 0, then that value is a local minimum. And there's one awkward case. If that function, the second derivative function, turns out to equal 0, then we can't make any immediate conclusion using the second derivative test. Requires some further work. So here are some examples. Here we have polynomial function. It's a polynomial of degree 4. What are the critical points of this function, and are they minima or are they maximum points, or can't we tell anything? So first of all, form the first derivative. We have 4 times x. We have to subtract 1 from the power, so we get 4x cubed minus 6 times x. So here's our first derivative function. The next step, we have to identify all of the input values for the first derivative function under which it becomes 0. And it turns out that this function has 3 critical points. There are 3 solutions, 3 values of x under which this becomes 0. And these are x equals 0. If we put 0 there, we get 4 times 0 minus 6 times 0, which is equal to 0. The 2 other critical points are plus or minus the square root of 1.5. I'll leave you to confirm that if we put that value into this expression, then the outcome will be 0. We want to determine what the nature of these critical points are. So we have to find the second derivative. So in other words, we differentiate this function. And it's the same sort of process. 3 times 4 gives us 12. We subtract 1 from the cubic term. That gives us 12x squared. The first derivative of minus 6 times x, that's just minus 6. So the second derivative function for our initial function is just 12x squared minus 6. So now what we have to do is to look at how this function behaves for each of these 3 critical points that we've discovered. And we start off with the easy case. When we put 0 as an input to the second derivative, what do we get? We get 12 times 0 minus 6, which is negative. That's all that matters here. So the critical point is 0. That's a local maximum. In the other 2 cases, these turn out to be, when we evaluate this function involving these 2 critical points, in both cases the result that's returned is 12, a positive number, so both of these points are local minima. Now if we look at that on the diagram, this is a function I put on one of the earlier slides. So here we have our 2 local minima points, the points corresponding to positive or negative, the square root of 1.5. And here we have our local maximum point, the point x equals 0. Let's look at a slightly more complicated example. Suppose our initial function isn't just a simple polynomial, something involving the logarithmic function. then in that case, what's the first derivative of this function? Well, we saw in the last lecture, if you look at the table of examples, the first derivative of log x is 1 over x. The remainder, we have 3 times 25, 75, log x squared. Similarly with this function, so we simplify it, the first derivative of f of x, in this case, turns out to be this function here. We want to look at the cases when that function takes the value 0. Now, one simplification we have is we only need to look at the function that's given by the numerator here. We don't have to worry about this term on the denominator. That's not going to be contributing. So, if we do that, if we look at when the numerator of this function takes a value 0, it turns out we can simplify that expression to this expression here, and we can look at when that equals 0. And it turns out there are two cases. The first of them, when x is 1, because the logarithm of 1 doesn't matter what the number base is, the logarithm of 1 is always 0. So that gives one of our critical points. The other critical point we find by looking at this factor here, and it turns out that when we set x to be the exponential function raised to 1.2, this term here becomes 0. We want to determine which of those, what the nature of those critical points is. Well, this is one example where we run into a problem. We have to look at the second derivative. And if we take the first derivative of this function, one thing that happens is the value of that function on one of the critical points turns out to be 0. So we cannot say whether it's a minimum or a maximum point. Again, I'll leave you to work out why it's the case that the second derivative in this case on the critical point 1 turns out to be 0. All right. What about the other critical point? I'm not given the other horrible looking expression for the first derivative of this function, but it turns out the second derivative of this function on this particular critical point is input. That turns out not to be 0. In fact, it turns out to be negative. So that corresponds to a maximum. If you look at this section of the course textbook, there are a number of worked examples given of using first derivatives to solve optimization problems and applying the second derivative test. So let me just summarize things. The concept of critical point and their analysis, this is an extremely important notion in the subject called optimization theory. This is one of the specialist areas that you'll have a chance to see in more detail in the final year of computer science, in particular on the module Comp 331. There is a problem with the techniques I've been talking about in this lecture, and that is, in some ways, they're not very realistic because they only involve fixing a single parameter. In a more realistic setting, in solving an optimization problem, one may have to find the best setting for several variables at once. And that is the extension of basic differential calculus that I'm going to look at in the next lecture.